same, a constant change in y over a constant change in x, right? That ratio doesn't seem to be the same. So, since it's not linear, I'm guessing based on what we did in the notes, it must be quadratic. There must be a square involved here. I know it's hot in here, I can't help it. Now, let's go to our calculator. And let's go to stat. Everybody find the button that says stat. Okay. And when you hit stat, it's automatically on edit. Stat's right here. Look where I'm pointing with my little finger.
Oh,
Right there, it says STAT right on it, yep. So when I press that, there's lots of options, but the one that's highlighted is edit. Edit means you're gonna put in data, so go ahead and press enter. Now, does anybody already have data in there? Okay, those of you that don't, just hang on. If you do have data in there, go back to stat.
Oh wait, I typed in the, never mind.
Oh, okay. All right, never mind then. I don't need to talk about it then if nobody has it except me, so I gotta get rid of mine.
When you hit 4 though, that's clear list.
Yeah, but then you gotta tell it which list to clear.
Okay.
So it'd be L1, L2. In my case, I don't know how yours is set up. Okay, so now I'm in edit, and you should have a column that says probably L1 and another column that says L2. So you're gonna type in, these are your L1s and these are your L2s. Make sure you correspond them. So make sure 4 is across from 20 and so on. So we're just putting in the data right now. We're gonna let the calculator find the equation for us. Hopefully he will.
Do we hit enter or after?
After you got enter, hit enter to after you put the last one in. Don't do anything else. Okay, does everybody have them in? Okay, so second quit. So second quit. Look where I'm pointing, they're right next to each other. Second quit. So now you're back to your regular home screen. So go back to stat. Go over in the top menu to where it says calc. And then go down to where it says quadratic regression. Because we had figured out it was not going to be linear. So it must be quadratic since those are the only two we've ever talked about. Press enter. I had to press enter twice. I don't know if you did or not. What came up when you did that? It says A equals, oh, you need to go down to calculate. I'm sorry, on the new calculators, just arrow down to calculate. And press enter. Yeah, so on the new calculators, I'm sorry, when you did that, you have to go all the way down to your calculate. And then it should come up, did it come up with an A, B, and C value for you?
Yep, why?
So remember that a quadratic looks like this. That's what a quadratic looks like. So the calculator just told you what your A, B, and C are. So your equation is 1x squared plus 1x plus 0. So this is the equation that fits that data. Okay? Now, you're welcome to come back after school if you need a little more help on that. We don't have time to dwell on that. But that's how, if you can't figure out by looking at the data what the equation is, and this is a hard one, then you can always let the calculator do the work. It will do it. If you think the data is linear, then you wouldn't, when you did when you did stat, calc, you wouldn't do quadratic regression, you would do linear regression. If you thought the data was linear. This one clearly isn't. These are not rising the same ratio. Okay, all right, so that's that. All right, so that was a homework question, so now that one's done. Now, let's get our notes out, and let's see where we're at here. By the way, that date is in there forever now until you either replace it with new data or clear it out. It'll stay there for days and days. In case you want to come back and redo that problem. All right, so here we go. I think we're ready for problem number 3 in part 1.2. Are you with me? All right, so it says consider this function. You are going to answer about a bazillion questions, but before we answer any of them, what does this look like? Tell me what you think this looks like. Okay, so Robbie goes like this. He's on the right track because when he sees an x squared, he knows it's a parabola. Every x squared you ever draw is going to be a parabola. Now, this particular parabola happens to have a negative in front of it. So what does that do to it? That turns it upside down. So you've got your upside down parabola, but you added 3 to it. I'm writing it in that order because sometimes that's easier. What happens when you take your upside down parabola and add 3? It goes up 3 units. So, this is what it looks like. Anytime you take a function, whether it's a parabola or not, anything, and you tack a +3 on the end, that's going to move it up 3 units. If it were a -3, it would move it down 3, right? Any number on the end like this. Okay, so let's answer some questions. Here's your picture. Would you say that it's continuous? Yes. And I'm going to go ahead and just add from negative infinity to infinity because that tells me it's continuous on the whole thing, the entire thing. If you don't add that, I'm not marking it wrong. I'm adding that because I'm a math teacher. Increasing or decreasing? Now remember, when we make this decision, it's left to right. So if you put your pencil right here and you move that direction, what's happening? It's increasing till it gets to here, and then it is decreasing. So we are increasing from negative infinity to 0. You're moving left to right. So you're judging x values. Left to right, those are x's. So as I go from negative infinity to 0, my pencil is going up. But as soon as I get to 0, my pencil is going down. Okay? All right. Bounded, above, below, and bounded. Now, bounded above. Remember, that means it has a ceiling. It has a point beyond which it doesn't go any higher. Does this one have that kind of situation? Yeah. Yes. It is bounded above at y equals 3. Y equals 3 is the highest point on the curve. Now notice, when I was talking about increasing and decreasing, I was using x values. because increasing and decreasing is a movement left to right. Boundedness is above and below, which is a Y, right? So we're bounded above at Y. Are we bounded below? Is there a floor? Oh, see these arrows right here? That's just gonna keep on going, right? So no. Is it therefore bounded? No. The only way you can be bounded is if you have both a ceiling and a floor. This one does not have a floor, so it can't be considered bounded. When someone says to you, the sine curve is bounded, what that means is it has a max and min that it doesn't go past, bouncing back and forth between those two.
Do you want us to write all of those and like answer none, or can we just write what is true? Like,
Oh, you can just say what's true.
okay.
Okay. Asymptotes. Now look at that picture. Remember that an asymptote is a line that the curve approaches but doesn't intersect. These are asymptotes. Does that picture have anything like that? No. If it had an asymptote, you'd see it. It'd be part of the picture. There is no asymptote. Does it have a maximum and or minimum? It has an absolute minimum. Maximum. At 0,3, right? That's its absolute maximum. Does it have a minimum? No. It goes on forever, down infinitely forever. Does it have any symmetry? We're going to talk a lot about symmetry here in a minute, but just based on what you know about parabolas, does that have any symmetry? Yeah. What's it symmetric about or across? The y-axis. So it is symmetric about the y-axis. And I don't know if I've given you this vocabulary or not. If you have y-axis symmetry, you're called an even function. Have we talked about that yet, even and odd? All right, I'm telling you even. Even means it's symmetric about the y-axis.
And odd is of the
Origin,
origin.
origin, odd origin, that's easy to remember, that one. We don't have that here though. This one is not odd. It is possible for things to be even and odd, but they usually aren't functions if they're even and odd. Okay, we'll talk more symmetry. We're going to talk a lot about that in a minute. Domain, range, and zeros. Domain, range, and zeros. So look at your picture. Domain, range, zeros. Okay, domain. Tell me about the x values in that picture. What did you say?
Negative infinity to infinity.
Yeah, everything. In the old days, you called that all real numbers, right? Goes forever, left and right, never stops, no breaks. How about range? Kamara says negative infinity to 3. Did you put parentheses here or bracket? Should be bracket, but otherwise you're exactly right. That's your range, because that point's included, right? It does go up to 3, and then everything below it, so you're exactly right. What do we mean by zeros?
Where it crosses.
Where it crosses the x-axis? Okay, now these would be the zeros. On my sketch, that's absolutely impossible to tell. So let's go back to our equation. And remember that if I am crossing the x-axis, isn't my y equal to 0? So I'm going to set my equation equal to 0 and solve it. Did you get plus or minus root 3?
Oh, yeah. I did it on my calculator.
Mm-hmm. And you got the,
It's like 1.735.
Yeah. You got the decimal approximation. If you have to do it exactly, this would be called the exact answer, because it's not rounded off, then you would just solve your little quadratic equation. Does that make sense to everybody? All right, I want to just take a minute. I don't know that we'll do all of these supplemental problems, but I definitely want to do some of them because we need to have a grip on the various special symmetries. This one was symmetric about the y-axis. That is definitely one of our special symmetries. We'll look at some other ones too and talk about the tests of symmetry. Okay. So everybody ready? The special symmetries are, write these down, a y-axis, and we just had an example of that. Above y-axis in parentheses, write even, because if it has that symmetry, it's even. Another special symmetry is x-axis. No name for that, x-axis. Another special symmetry is the origin. And I already told Jake, if it has that symmetry, if it's symmetric about the origin, it's odd. So above that, write odd. And then the last special symmetry is the line y equals x. And above that, just write identity. That is called the identity line, y equals x. In case you, oh man, in case you forgot, the line y equals x looks like this. It's that perfect diagonal through the origin. Okay, so those are your special symmetries. So, find the special symmetries for y equals 3x. So what I'm going to do right now is I'm going to go through this problem with you, and I'm going to show you all the tests of symmetry for all the special ones. So we'll do it in the order we wrote it down. So we started with y-axis. To test for symmetry across the y-axis. Okay, so we had a picture of our parabola and you just eyeballed it and said, yeah, that has symmetry. But what if you don't have a picture, or you can't tell from your picture? What if you have some random equation? The test for symmetry about the y-axis is change the sign on x. Because if I'm the y-axis, if you go from this side of me to this side of me, you're changing the sign on x. Right? This might be -2 and this would be +2. So what does that look like? Well, go to your equation and make x negative. That's all. And then simplify that and ask yourself, is that the same as the original problem? No. So this one does not have symmetry about the y-axis. This is not an even function. If it were, then when I change the sign on x and simplify, I would end up with exactly what I started with. All right, I've got an x-axis next. What do you think the test for symmetry about the x-axis is? Change the sign on y. So go back to your original, make it -y equals 3x. Simplify a little bit, clean it up a little bit. Is what I got the same as the original? Nope, don't have any symmetry there either. Okay, the origin next. Origin. Change the sign on both. So then my equation looks like negative y equals 3 times negative x. Now clean it up. You have to simplify it. Oh my gosh. Does that end up like the original? So this one has symmetry about the origin, therefore it would be classified as odd. So maybe the question says find the symmetry, that's what we're doing. Maybe the question says, is this guy odd? Well, if you're testing odd, this is the only test you have to do right here. Right? And then finally, the identity. To test for symmetry about the identity, you switch x and y. So in other words, instead of y equals 3x, it's x equals 3y. When I get y by itself, is that the same as the equation I started with? No, believe it or not, there are functions that work that way. This is not one of them, so that would be a no. So the only special symmetry that this one has is the origin. When Mrs. Ford makes up equations, chances are they'll have no symmetry at all. Most functions out in the world have no symmetry. This one happens to have symmetry about the origin. Did you have a question? Is it an emergency? Okay, if it's not an emergency, then no. If it's an emergency, go. Leave your phone here. But if you're gonna hold it, hold it. All right, let's do one more. Which one would you like to do? B, C, D, or D? Oh gosh, there's some on the back too. Which one, C?
C.
All right. So. All right, so C, our equation is x squared plus 3. All right, let's change the sign on x. So y equals negative x squared plus 3. Notice I put that in parentheses. You have to replace x, whatever's happening to x is now happening to negative x, so it's going to be squared. Negative x is squared. Is that the same as the original?
Yeah.
Yep. So this one is even. Some of these I think you can probably tell, especially after you practice a bit. If I change the sign on y, is that going to be the same equation that I started with?
No.
Isn't it going to be negative x squared minus 3? Which is not the same as what I started with? So that's a no.
Do you still need to go through all of them though, when you find one?
Oh yeah, because you can have multiple symmetries, yeah. Yeah, we'll turn the page and do a couple on the back and you'll see what I mean. All right, changing the sign on both. What do you think about that? Isn't this negative gonna disappear? No. But this one isn't. So that's another no. Are you guys keeping up with this? All right, let's do the identity. Switch x and y. Oh, this one's obvious. That's not the same equation, right?
Yeah.
So this one only has symmetry about the y-axis. All right, let's turn it over. Look at some of these ones on the back. Now, I pointed out that E and F are not functions. We can still test for symmetry though. So let's do one on this page.
G.
G.
It's on my extra page.
No, I agree.
equals negative 1 over x. Alright, so just going in the same order we did before. Y-axis says change the sign on x. So if I change the sign on x, I'll have y equals negative 1 over negative x, which will be y equals 1 over x. Symmetry about the y-axis. Alright, now change the sign on y. I don't think I have it there either, do you? Don't let me pull a fast one. Amanda's agreeing with me. Change the sign on both. So negative y equals negative 1 over negative x. A lot of negatives in there. Uh-oh. I think that one works. So this guy is odd. He definitely is odd. He has symmetry about the origin. Now switch x and y. So x equals negative 1 over y. Now if you're at all confused, just rearrange this and get y by itself again and see if it matches the original. So if I multiply this over, I have yx equals negative 1, and then y equals negative 1 over x.
Oh, yeah.
Whoa.
Same thing, right? So this one has two symmetries, the origin and the identity. Okay, do you think you have the hang of that? So that at some point, if I asked you which symmetry something had, you would be able to do it. The hardest part is going to be you gotta memorize the rules. The tests. Think you got it? You wanna do one more or not? I don't wanna bore you out of your mind. It's not quite as exciting as it was yesterday. What? Are we good? All right, let's see what's on the next page then. Okay, number 4 we already did. Even and odd. What's even? Symmetry to the y-axis. What's odd?
Origin.
Symmetry to the origin. Yep, perfect. So you just need to remember that if you are asked, is this function odd, then you're going to do what we did here, only you'll only do this one. Because odd is the origin, right? So being even or odd is a test of symmetry. You're going to do one of the tests. Okay, number 5, find the domain.
Miss Ford?
Yeah.
Well, what would be symmetry to the origin look like compared to like the axis? Because when that, is that just saying it's symmetric over both?
This curve is symmetric over both because this particular equation, the equation we started with, looks like this.
Okay.
And here's the identity line. So does it make sense to you that if I fold it across the identity,
Okay.
it would land on top of itself, right? Does it also make sense to you that every point here in quadrant 2 is reflected into quadrant 4 with this particular shape? Okay, so let me just pause for a second. Can I think of one? Yes, I can. I can. So let's consider, okay, here's my identity line. Okay, so let me consider this picture right here, this black line. Okay? Now, use your imagination, but if this is the point right here, if this is the point 1, 4, this would be the point -1, -4. Notice both signs changed. This black line has symmetry about the origin. It does not have symmetry across the identity, because if I creased my paper right here, that black line would actually end up on, that's supposed to be a straight line, on the blue line. So here's an example of one that has symmetry about the origin, but not the identity. They don't always go hand in hand. Okay, yeah. All right. Anybody else before we move on from the symmetry conversation, which is a great conversation? All right, so now we're gonna talk about domain. And we're all gonna try to stay focused. I know it's hotter than heck in here. I don't know what to say. Okay, so find the domain. All right. I want to just mention two things to you. When God created functions, He gave them the domain of all real numbers. That's perfect. But then man got involved and started screwing around with these equations, and then the functions domains got messed up. Does anybody know what will mess up a domain? There's really only two things that will mess it up. Drew? A hole? Yes, and how would a hole be formed? A hole will mess with your domain. How is a hole formed? It means there's an X value that's not possible. So think of an equation. How would you have X values that aren't possible?
An asymptote?
An asymptote? Where do those, that reflects an X value that's not possible. In an equation, how do you get X values that aren't possible? Like when I look at this equation right here, every X is possible. So this domain is perfect. This is everything. What happens, Nyla?
Like on the bottom one, if the X was equal to 3.
Exactly. So one of the domain issues is your denominator can never be 0. So write this down and highlight it. The denominator can never be 0. If you put a denominator into your problem, you're putting in potential issues, okay? So I want you to look at this problem B. It has an issue. It has a denominator, right? So Nyla, what did you say X can't be in this problem?
3.
Would everyone agree X can't be 3?
Yeah.
So how do I express that? X can't be 3 is kind of, that's the meaning of it. How do I write that as an interval now? Think about it on the number line. It's the whole number line except for 3. So how would I write that, Charlie?
Would it be negative infinity to 2?
To 3.
To 3, and then
3
it's
to
3 to
infinity. So Charlie, remember that here's 2. In between 2 and 3, there are a ton of numbers. So we want to run it all the way up to 3, put a parentheses because that dot's not included, and then start it again. So this describes everything except 3. Would you agree with that? All right, there are 2 things that screw up your domain. One is a denominator. Every single time you have a denominator, you're going to have a potential issue. So let's look at problem C. You have 2 denominators. So guess what? X can't be 0 or 3. So think about on the number line, at 0 and 3, you're not included. Everything else is included. So how would we express that as an interval?
Negative infinity to 0.
Yep.
Median 3 to positive.
Well, be careful. How about 0 to 3?
I'll do.
Can't we be in here too?
Oh, we could be in there too?
Yeah.
Oh, so
Yeah.
then.
We can be
3,
everywhere except
0 and 3.
0 and 3.
Okay.
So we can be to the left, we can be in between them, and we can be to the right. X can't be 0, X can't be 3, X can be anything else.
Okay.
Numerator. Only the numerator.
Now,
Nothing
D, lordy, lordy, lordy.
like to write the
Let's look at D.
you don't have to do anything.
Okay. Now, we already know denominators can't be 0. So clearly, X cannot be -1. I'm gonna go ahead and just put that on my number line right now. X can't be -1. What about this?
1 or -1? Is that how you do it?
Well, think about it, Jake. If you put 1 in here, does that equal 0? Is there anything you can square and add to 1 and get 0?
Is it I?
Well, it could be imaginary, but we're keeping it real, all right? Everything's real here. We don't want any eyes. Certainly, if you put an eye there, it would give you a 0, but we're not, we're on a number line,
Okay.
okay? This will never be 0 in real number land. Square it and add 1. Won't it always be positive? Okay. So the only issue from the denominator is -1. We got issues up here though too, guys. Because we just said we're keeping everything real, which means your radicand, and the radicand is what's under the radical sign. The radicand must be greater than or equal to 0. That's another domain breaker. You couldn't, for example, in this problem, could you put in 7? No, because if you did, it would be imaginary. So the only numbers you can put in are the ones where this guy is positive. So if my arithmetic is right, I'm saying X is less than or equal to 4. So my domain is all the numbers less than or equal to 4, except -1, because I already blocked that one out. Right? We said X couldn't be -1. But now X has to be less than or equal to 4, so what's this answer going to look like? Negative infinity to -1, or -1 to 4 with a bracket up here.
And then would you try to do the positive infinity?
No, because remember, you have to do less than 4.
Oh, yeah, okay.
I always use a number line to keep track of it. You don't have to, obviously, but I always do. 2 things disrupt your domain: a denominator and a radical. If you don't have a denominator and you don't have a radical, then except for weird exceptions, your domain's gonna be negative infinity to infinity. Because denominators and radicals are what mess it up. Okay, let's try the next one. Can you try the next one on your own? With your partner maybe? Talk about it? With enthusiasm and zeal. Cause you guys have math talk over there, or you talking about something else?
I was asking a question about the problem.
Oh, good, good. Did she answer?
Yeah.
Even better, super. All right, so Katie, since you're the resident expert over there against the wall, what did you guys decide about this problem?
Is it bracket -3 to 2, parentheses, to infinity, parentheses, on that one?
Like this?
Yeah.
Okay, that's Katie's answer. I have no idea, I have to look at it. So, first of all, she has an open dot at 2. See that, how that 2 is open? Perfect. Because what's our rule? The denominator cannot be 0. So she's right on target there. Then, I have a radicand. My rule says the radicand, that's this guy right here, has to be greater than or equal to 0, which means x has to be bigger than or equal to -3. So she said, okay, -3 is over here, I gotta be bigger than or equal to it, but skip over 2. Is that what she described right there? Beautifully done. Beautifully done. Does anybody have a question about that? Did anybody else, besides that side of the room, anybody else get that? Did you? Good job, good job. Well, what about this one? Have you had a chance to look at this one yet? Notice, this one does not have a radical in it. So I don't need to worry about rule number 2. I only need to focus on rule number 1. What do you notice about this? X can't be what? 2 or -2. So if you can't be -2 or 2, but you can be everything else, can you write that? -infinity, -2, or -2 to 2, or 2 to infinity. And last but not least, we're only gonna do a couple more things, guys, and we'll be done. Last but not least, this last problem. No radical, so I don't need to worry about rule number 2. Gotta have a radical to worry about this. I do have a denominator, but I want you to look closely at that denominator. Remember, the rule says it can't equal 0. What do you think about that denominator? It can't equal 0. It can't. Now, if you need to solve it out, go ahead. But what's gonna happen? Isn't it gonna get imaginary? So it's never gonna equal 0 in real number land. So what's your domain? All real numbers. Absolutely. So the presence of a fraction does not guarantee, some weird domain. In this case, it didn't matter because the denominator could never be 0, so the domain is still all reals. All right, we're gonna do one more section, and it's an easy one. You guys have done great. You've been really good. You learned a lot today. Talked about a lot. Vertical line test. Is it a function? Okay. Do you remember the thing called the vertical line test?
Yes.
Okay, so this should be easy. Is A a function?
Yes.
Yes. Because when I pass vertical lines down through, or sometimes we use our pencil, I don't hit anything more than once, right? You guys know what I'm talking about, vertical line test?
Yeah.
Okay. How about B? Nope, not a function. Doesn't pass the vertical line test. Oh, Lord. C's a little harder. It's easy when there's a picture. What do you think? You can do this a couple of different ways, but one thing I'd like you to just think about is, we talked earlier, we had an equation like -x² plus 3, and you told me that was a parabola. Anytime you have a square as your highest power, it's gonna be a parabola. If the x is squared, it's up or down. What if the y is squared? It's sideways. So if you can remember that, y squared is always a sideways parabola, then you can answer this question. Does a sideways parabola pass the vertical line test? No. No, it does not. How about D? What shape is D? It's a line. Think about lines, kids. Do lines pass the vertical line test? Yes. The only lines that don't are vertical lines, but their equation is x equals 5 or something like that. So D is a yes. It's a linear equation. It passes the vertical line test. All right, I'm going to stop there. You guys are on overload.